Tonight, we're going to let our thoughts wander and answer a quiet and enduring question. Does the past still exist? When a moment slips away from us, has it vanished entirely from the universe, leaving behind nothing more than fading memories and physical echoes? Or does the framework of modern physics suggest that every single event that ever happened remains permanently anchored within the grand geometry of spacetime, even if we can no longer step back inside it? Before we let our minds drift too far into the currents of this mystery, take a brief moment to settle into your favorite chair, pull up your blankets, and let the outside world fade away. Let us begin our slow exploration of the nature of time. Human experience divides our days into three distinct realms. There is the past, which feels finished, written, and unchangeable. There is the future, which appears open, hazy, and uncertain. And nestled precariously between them is the present, that narrow, vibrating edge of reality that feels overwhelmingly real. This tripartite division feels so fundamental to our daily lives that it is almost impossible to picture existence operating in any other fashion. The present is where we feel life actually takes place. The past survives only through the fragile medium of memory, physical consequences, historical records, and lingering evidence. The future exists purely as anticipation, hope, or worry. We remember yesterday, navigate today, and wonder about tomorrow. Yet even this straightforward structure conceals a deep and subtle puzzle. The present moment never seems content to sit still for long. A fraction of a second arrives, swells into a vibrant now, and instantly dissolves into what has already been. The sound of a spoken phrase evaporates into the air almost as soon as the lips stop moving. A physical action begins, unfolds, and instantly becomes history. The present feels entirely solid, yet it resists all attempts to hold it in place. This gives rise to the familiar mental image of time as a relentless river, carrying us steadily forward. Events loom on the horizon of the future, drift through the fleeting window of the present, and vanish behind us into the dark waters of the past. We talk about time as though it were an active traveler, telling one another that it flies by, drags heavily, or occasionally runs out when we have too much to do. But when a moment officially concludes, what has actually left the universe? Over 16 centuries ago, St. Augustine wrestled with this very perplexity, noting in his Confessions that time feels wonderfully intuitive until for a precise definition. We rely on time continuously. We schedule our lives around it, synchronize our clocks by it, divide it into neat hours and minutes, and lament its scarcity. Yet, defining what time actually is remains deeply elusive. One crucial realization often escapes our notice when we think about this. An event that is no longer happening is not necessarily an event that has completely ceased to exist. Think about a conversation you might have shared with a friend yesterday. It is certainly not happening right now. The voices are quiet, the participants have gone their separate ways, and that exact exchange cannot simply be picked up mid-sentence without context. But does that mean the conversation has been entirely erased from reality? Or does it remain firmly embedded within the history of the world, fixed forever within the sequence of occurrences that led to this very moment? The same strange quality applies when we reminisce about a childhood home. Perhaps the physical building still stands on its familiar street, but the home as it existed during those early years has fundamentally transformed. The furniture has been rearranged or replaced, the walls have been repainted, and the people who filled those rooms have grown older or moved away. The specific arrangement of sounds, light, objects, and relationships belongs entirely to an earlier epoch. That version of the home is no longer present, yet its quiet effects ripple outward into human memory, personal habits, emotional patterns, and even the subtle physical wear and tear left upon the structure of the house itself. Light itself makes this contemplation even more astonishing. When we gaze upward at the sun on a clear day, we are not seeing it as it is at this exact second. We are seeing it as it was roughly 8 minutes ago, because sunlight requires finite time to bridge the vast vacuum separating the sun from our eyes. When astronomers turn their telescopes toward the distant Andromeda galaxy, they capture light that commenced its long voyage approximately 2.5 million years ago. The radiance entering the telescope lens is not a live broadcast of what is happening in Andromeda right now. It is a messenger from the distant past, arriving in our present moment. That past is gone in the sense that those specific stellar events are no longer occurring at their original coordinates. Yet, their electromagnetic radiation continues its tireless journey through the cosmos. A pulse of light launched millions of years ago can cross an observatory detector tonight and register a tangible, measurable trace. The physical universe is brimming with such traces. Memories persist within the shifting patterns of neural connections and electrical activity inside the brain. Ancient climates whisper their stories through chemical signatures trapped deep within polar ice cores and lake sediments. Biological organisms carry genetic instructions passed down through unbroken chains of reproduction. Fossils preserve the altered stone impressions of creatures that perished millions of years ago. Impact craters punctuate planetary surfaces, tree rings chronicle passing seasons, and distant starlight paints the night sky. Even the ordinary objects in our immediate surroundings are saturated with the history of the past. A drinking glass sitting quietly on a table occupies its specific position because of a lengthy chain of preceding causes. Someone manufactured it, packaged it, shipped it, poured liquid into it, and placed it on that exact wooden surface. The past may not be fully visible, but the present would be entirely impossible without it. Of course, a trace is not identical to the event that generated it. A photograph of a violent thunderstorm is not the storm itself, and a memory of a beloved voice is not the voice speaking anew in the room. Evidence proves that something happened, but it does not automatically reveal the exact ontological status of that past event. Human consciousness experiences a moving present, moving relentlessly forward while carrying memories of what has come before, yet lacking any intrinsic memory of what is yet to unfold. Physics, however, approaches this dilemma from a different angle, seeking descriptions of nature that remain consistent for observers moving in diverse ways and viewing events from separate vantage points. This introduces a deep tension between our inner experience and our scientific models. Experience tells us that reality constantly updates itself, with each new present replacing the one before. Physics asks whether that sharp division between past, present, and future is an intrinsic feature of the universe itself, or merely a byproduct of how conscious minds happen to experience the passage of time. For a vast stretch of human history, time was pictured as a universal backdrop shared equally by everything in existence. The sun traced its path across the sky, seasons turned in orderly succession, shadows lengthened, and all events seemed to unfold within one grand, shared timeline. Different societies might adopt different calendars or debate the precise hour, but those variations were viewed as practical conveniences rather than fundamental truths. Beneath imperfect human measurements, philosophers and scientists alike assumed there existed one true, objective time. Aristotle linked time directly to motion and change, describing it as a measure of alteration in relation to before and after. Other traditions viewed time as a cosmic cycle, or an indifferent stage across which the drama of the universe played out. Despite these varied perspectives, everyday intuition reinforced the comforting belief in a single universal present. The scientific portrait of time gained remarkable clarity during the work of Galileo Galilei. By studying falling bodies, swinging pendulums, and projectiles, Galileo helped demonstrate that motion could be captured through mathematics. Time emerged as a measurable quantity that could be plugged neatly into physical equations. If an object's starting position and velocity were known, its future trajectory could be calculated using a temporal scale assumed to apply uniformly across the universe. Isaac Newton cemented this view during the 17th century. In his monumental treatises on motion and gravitation, Newton drew a sharp line between ordinary measured time and what he termed absolute, true, and mathematical time. In Newton's vision, absolute time flowed onward by its own internal nature, utterly independent of clocks, planets, human observers, or physical changes. A clock did not create time, it merely attempted to measure it. This distinction was vital because real-world clocks are inherently imperfect. Pendulums are influenced by ambient temperatures, mechanical gears wear down over time, sand trickles unevenly through glass bulbs, and even the rotation of the Earth fluctuates slightly. Newton's absolute time was therefore an ideal, transcendent background against which every physical clock could be judged. Within the framework of classical mechanics, the entire cosmos shared this singular background. At any chosen instant, every physical object possessed one definite position and one precise velocity. The moon, a falling autumn leaf, a ship navigating an ocean, and a stone rolling down a hillside all participated in the exact same universal moment. This made simultaneity appear wonderfully straightforward. Two events were considered simultaneous if they occurred at the same absolute moment in time. Observers might receive news of these events at different times because light and sound required finite intervals to travel through space, but those delays were treated merely as technical measurement problems. Once signal travel times were accounted for, everyone could theoretically agree on what happened simultaneously. The universe thus resembled an immense theatrical stage. Space provided the physical setting, while time supplied the steady rhythmic tempo. Matter moved through both arenas according to immutable laws. The scenery might shift, but the stage itself remained completely untouched. Clocks were regarded much like spatial rulers. Just as a ruler measures distance without altering space, a clock was assumed to measure time without being fundamentally altered by its own motion or location. A clock carried up a mountain or placed on a moving ship was expected to tick away at the exact same underlying rate, provided it remained in good working order. This classical framework fits seamlessly with presentism, the philosophical view that only the present moment possesses true existence. Under presentism, the past has been entirely erased, the future does not yet exist, and reality is restricted to a universal now that advances step by step, discarding each moment as it replaces it. The disappearance of the past feels uncomplicated under this assumption because yesterday's state of the universe is superseded by today's state, rendering yesterday entirely unreal. Classical mechanics reinforce this perspective because of its staggering predictive power. Newton's laws successfully explained planetary orbits, tidal movements, pendulums, and countless mechanical systems. The mathematics could accurately forecast the return of a comet or the arc of a cannonball, uniting the force pulling an apple toward the ground with the gravity holding the moon in its celestial path. This monumental success made absolute time feel less like a theoretical model and more like pure, undeniable common sense codified into equations. Yet, a hidden limitation was embedded within that very success. The speeds encountered in ordinary daily life are extraordinarily slow when compared to the speed of light. A racing train, a high-altitude airplane, and even the Earth hurtling around the sun move at only microscopic fractions of light speed. Gravitational variations across familiar terrestrial distances are similarly minuscule. Under these gentle conditions, the subtle corrections later demanded by relativity are so vanishingly small that they can safely be ignored in everyday calculations. A person walking across a room does experience a slight relativistic shift in elapsed time, but the difference is far too tiny for any conventional clock to register. Classical physics worked brilliantly, not because it captured absolute reality with flawless precision, but because it served as an exceptionally close approximation within the narrow band of human experience. The universe kindly kept its stranger behaviors hidden until scientists began investigating electricity, magnetism, and high-speed motion with unprecedented accuracy. As long as one universal present is taken for granted, the past can easily be dismissed as a discarded state. But if observers can no longer agree upon a single shared present, the boundary separating what currently exists from what has vanished becomes extraordinarily difficult to maintain. By the 19th century, physics had constructed two wildly successful pillars. Newtonian mechanics governed moving matter, while electromagnetic theory explained electricity, magnetism, and light. Each framework reigned supreme within its own domain, but tension mounted when scientists attempted to harmonize them. Classical mechanics dictated that speeds should combine in a straightforward, additive manner. If a passenger walks forward inside a moving railway carriage, an observer standing safely beside the tracks simply adds the passenger's walking speed to the speed of the train. If the passenger reverses direction, the speeds subtract. It is a rule so intuitive that it requires no thought. Light, however, stubbornly refused to play by these rules. During the 19th century, James Clerk Maxwell unified electricity and magnetism into a cohesive mathematical framework. Maxwell's equations demonstrated that fluctuating electric fields generate magnetic fields, and fluctuating magnetic fields in turn generate electric fields, allowing these linked disturbances to propagate through space as electromagnetic waves. When Maxwell calculated the velocity of these waves, the numerical result matched the known speed of light. This stunning revelation proved that visible light is merely one narrow band of electromagnetic radiation, sharing a common family with radio waves, microwaves, infrared rays, ultraviolet light, X-rays, and gamma rays. The equations specified one fixed speed for electromagnetic waves traveling through a vacuum, roughly 300,000 kilometers per second. At that velocity, a beam of light could circle the globe more than 7 times in the blink of an eye. This velocity immediately raised an uncomfortable question. A speed measured relative to what? Every wave known at the time required a physical medium to travel through. Sound waves propagated through air, water waves rolled across the ocean's surface, and mechanical vibrations traveled through solid ropes. It seemed entirely logical to assume that light must likewise require a supporting substance, which scientists dubbed the luminiferous ether. This hypothetical, invisible medium was imagined to permeate all of space, serving as the background substance through which light waves undulated, much like sound ripples through the atmosphere. If the Earth was constantly orbiting the Sun and thus plowing through this stationary ether, laboratories on Earth should encounter an ether wind. Light traveling in the direction of the Earth's orbital motion ought to behave differently from light traveling perpendicular to it, just as a swimmer's speed is affected by the flow of a river. To test this hypothesis, Albert Muchelson designed a remarkably sensitive optical instrument called an interferometer, which split a single beam of light into 2 perpendicular paths, reflected them off mirrors, and recombined them to check for interference patterns caused by tiny travel time differences. In 1887, Michelson and Edward Morley conducted a refined version of this famous experiment in Ohio, rotating their apparatus as the Earth traveled along its orbit. The anticipated shift in the interference pattern stubbornly failed to materialize. The Michelson-Morley experiment did not conclusively disprove every conceivable variation of an ether theory, but it utterly failed to detect the expected motion through a luminiferous medium. Light acted as though its measured speed remained completely indifferent to the direction of the Earth's travel. Physicists scrambled to rescue the ether concept by introducing ad hoc adjustments to physical matter. George Fitzgerald suggested that objects physically contract along their direction of movement when traveling through the ether, while Hendrik Lorentz developed a comprehensive set of mathematical equations known as the Lorentz transformations, showing how lengths, times, and simultaneity would need to warp as relative velocity increased. These adjustments were initially interpreted as physical strains occurring within objects moving through a stationary background medium. Albert Einstein took a far more revolutionary path in 1905. Rather than inventing elaborate reasons to keep the ether hidden, he dispensed with the concept entirely. Einstein's special theory of relativity rested upon 2 foundational postulates. The first declared that the physical laws of nature are identical in every inertial frame of reference, meaning any laboratory moving at a constant velocity without acceleration enjoys an equal claim to validity, with no single frame representing absolute rest. The second postulate asserted that every inertial observer measures the exact same speed for light in a vacuum, completely independent of the motion of the light source or the observer. This sounds utterly paradoxical if we cling to classical speed addition. Imagine a spacecraft rocketing directly toward a beam of light. Common sense suggests the spacecraft should measure the approaching light as traveling faster than it would for a stationary bystander. Yet special relativity insists that both observers measure the exact same numerical speed. The universe preserves this constant speed of light by forcing space and time themselves to adapt and flex. Observers moving relative to one another measure different lengths, experience different durations between events, and most crucially, disagree profoundly about whether spatially separated events happen simultaneously. Time dilation dictates that a moving clock accumulates less elapsed time between shared events than a stationary clock following a different path. Length contraction causes distances measured along the direction of motion to shrink relative to another observer. These phenomena are deeply intertwined consequences of the Lorentz transformations. While these relativistic differences are microscopic at everyday speeds, they become substantial as velocities approach the speed of light. Relativity does not merely claim that moving clocks look slow because light signals take longer to reach our eyes. After observers separate and directly compare their clocks, the devices will genuinely display differing amounts of elapsed time. Each clock measures its own proper time, representing the specific temporal duration accumulated along its unique journey through spacetime. This reality has been verified repeatedly using precision atomic clocks, particle accelerators, and satellite communication systems. Unstable subatomic particles known as muons survive significantly longer when hurtling at near-light speeds, allowing far more of them to reach the Earth's surface from the upper atmosphere than would otherwise be possible. Time is therefore not a uniform river flowing identically for everything in creation. The duration separating events depends entirely on motion and trajectory. Once this is understood, the comforting illusion of a universal master clock shatters permanently. There is no absolute background time against which all clocks can be synchronized. Different observers can record different durations without either clock malfunctioning in the slightest. The disappearance of the past once seemed trivial when everyone shared a single universal present. A moment existed everywhere at once before yielding to its successor. But once relative motion alters how observers carve up events into past, present, and future, the boundary of the now ceases to be universal. Light did much more than impose a speed limit on the cosmos. It dismantled the notion that the universe advances according to a single shared heartbeat. The most unsettling realization of special relativity is not simply that moving clocks tick at different rates, but that observers moving relative to one another can actively disagree on which distant events are happening right now. This principle is known as the relativity of simultaneity. It states that two distinct events occurring at separate locations, judged by one observer to happen at the exact same moment, can occur at completely different times according to another observer moving relative to the first. Neither observer is confused or making an error. Each is operating within a valid inertial frame, and special relativity provides no physical justification for elevating one frame over another as the preferred viewpoint of the universe. Einstein famously illustrated this concept through a thought experiment involving a high-speed train and a railway embankment. Imagine a long train gliding smoothly along a straight track. At the precise instant the midpoint of the train passes a person standing beside the tracks, lightning strikes both the front and rear ends of the train simultaneously, from the perspective of the railway observer, who sees the light flashes arrive at the exact same time. Now consider a passenger seated precisely at the midpoint inside the moving train. At the moment of the lightning strikes, this passenger is moving forward toward the flash at the front of the train and away from the flash at the rear. Because light travels at a fixed speed relative to every inertial observer, the passenger does not attribute the difference in arrival times to varying light speeds. Instead, the passenger receives the light from the front strike before the light from the rear strike, and thus concludes that the front lightning bolt struck first. The observer on the embankment says the strikes were simultaneous. The passenger on the train says they were not. This disagreement is not merely an optical illusion caused by signal travel delays. Both observers understand that light travels at a finite velocity, and both can mathematically correct for travel times using their own synchronized clocks and rulers. Even after accounting for these delays, they still assign different timestamps to the events. The discrepancy arises from the fundamental geometry of special relativity. To establish a network of simultaneous distant events, an observer must synchronize clocks using light signals, assuming light takes an equal time traveling in both directions. While this procedure works within a single inertial frame, clocks synchronized in one frame do not appear synchronized to an observer moving relative to it. Every observer carves out a unique set of distant events to label as the present moment. While these differences are imperceptible at the slow speeds of terrestrial trains, the principle holds true across all velocities. As distances and relative speeds scale up, the divergence becomes monumental. One helpful way to visualize this is to imagine spacetime as a vast, static map containing every event that ever was or will be. An observer slices this four-dimensional map into horizontal layers representing the past, the present, and the future. An observer moving at a different velocity cuts through that exact same map of spacetime at a slightly tilted angle. Both observers agree on the physical events themselves. They agree that lightning struck the train, and they agree on the physical scars left behind. But they organize those distant occurrences into entirely different slices of simultaneity. There are, however, strict limits to this disagreement. Observers cannot scramble the chronological order of events when one event has a direct causal relationship with the other. If a person presses a button and a connected lamp illuminates a fraction of a second later, every observer across the entire universe will agree that the button was pressed before the lamp lit up. These events are causally linked by a time-like or light-like interval, meaning a signal traveling at or below the speed of light can bridge them. Their causal sequence is sacred and preserved for all reference frames. An effect can never precede its cause simply because an observer happens to speed past. Chronology can only vary for events that are space-like separated, events occurring so far apart in space and so close together in time that no light signal could possibly travel between them. For such distant events, one observer might record the first happening earlier, another might record the second happening first, and a third might view them as simultaneous. This creates no logical contradiction because neither event could have exerted any causal influence upon the other. A dramatic illustration of this principle is the Andromeda paradox, popularized by physicist Roger Penrose. The Andromeda galaxy sits approximately 2.5 million light-years away from our planet. Because of this staggering distance, even the subtle motion of a person walking casually down a street on Earth alters which distant Andromeda events are intercepted by their changing surface of simultaneity. Imagine two pedestrians passing each other on a sidewalk, one strolling toward Andromeda and the other walking away from it. Although their walking speeds are negligible on a cosmic scale, relativity tilts their planes of simultaneity just enough that, when projected all the way across the universe to the Andromeda galaxy, the difference corresponds to events separated there by several days. In a thought experiment, this means one pedestrian's present moment might encompass an Andromedan civilization debating whether to launch a space fleet, while the other pedestrian's present moment lies slightly before that fateful decision was reached. Of course, this does not grant anyone on Earth the magical ability to peer through a backyard telescope and instantly spy on Andromeda's future, nor can a casual stroll alter alien affairs. The light reaching our eyes tonight left Andromeda millions of years ago, and any news of their current activities must still traverse the vast void at the speed of light. Nothing observable changes locally just because someone pivots and walks in the opposite direction. Nevertheless, the philosophical implication is profound. Strict presentism insists that only events happening right now truly exist, while the past has vanished into nothingness. Yet relativity destroys any universal consensus on what constitutes the present across the cosmos. If one valid observer judges a distant event to be happening right now, while another equally valid observer places that same event deep in the past, which perspective holds the absolute truth about existence? Special relativity refuses to crown a preferred reference frame. An event deemed past by one moving observer can be viewed as present or even future by another, provided the events are space-like separated. This challenges the simplistic idea that the boundary between an existing present and a vanished past can be drawn in a neat, universal way. While we experience a local present right here in our immediate awareness, the universe itself possesses no single cosmic now agreed upon by all observers everywhere. Special relativity ultimately revealed that space and time are not independent entities pasted together, but rather different facets of a single, unified, four-dimensional continuum. This profound geometric realization was championed by Hermann Minkowski, a mathematician who had once taught Albert Einstein. In 1908, Minkowski introduced a revolutionary framework uniting the three dimensions of space with the single dimension of time, forging the concept of spacetime. This was far more than a convenient visualization tool. It fundamentally overhauled the language of physics. In our everyday lives, we identify the location of an object by specifying where it resides. A book rests upon a desk, or a traveler stands beside a railway window. Yet spatial location alone is entirely insufficient to pinpoint a physical occurrence because the book may vanish from the desk by evening. A complete, unambiguous description requires both space and time. A specific location at a precise moment in time is known as an event. A lightning flash striking a platform, the arrival of that light at an observer's eyes, a clock ticking past midnight in a quiet laboratory. These are all events. Every collision, chemical emission, heartbeat, and quiet thought occupies a definite coordinate within spacetime. An object does not merely occupy a single point. As it endures through time, it traces out a continuous sequence of events known as a world line. Imagine marking a person's spatial coordinates once every second. Connected together through the geometry of spacetime, those marks form their unique world line. A stationary object traces a path that remains relatively fixed in space while stretching vertically through time, whereas a moving object traces a tilted path. Light itself carves out precise trajectories through this four-dimensional fabric, defining the ultimate boundaries of causality and connection across the universe. As we sit quietly with these thoughts, watching the boundaries of our own present moment gently dissolve and flow into the vast architecture of space-time, we are left to wonder whether anything is truly lost, or if all of our moments are simply waiting quietly within the eternal map of the cosmos. Light itself carves out precise trajectories through this four-dimensional fabric, defining the ultimate boundaries of causality and connection across the universe. As we trace these paths of light through Minkowski space, we encounter a geometric boundary known as the light cone, which separates the events that can influence us from those that remain forever beyond our reach. Every single point in space-time is surrounded by its own future light cone, representing the absolute limit of where any physical signal, particle, or flash of light can travel from that event. Simultaneously, pointing downward into the past, every point possesses a past light cone, encompassing all the events that could have possibly sent a causal message to this present coordinate. Everything outside these intersecting cones is permanently shielded from causal contact with the central event, existing in a realm where no information can pass. This geometric construction transforms our understanding of causality from a vague philosophical concept into a rigorous structural property of the cosmos. The past is not merely a collection of fading memories or historical documents left behind in the wake of our march. It is a physical region of space-time, located entirely within the past light cone of our current existence. Every event that has ever occurred, from the formation of the ancient stars to the quiet breath you took a moment ago, occupies a fixed, permanent coordinate within this immense four-dimensional landscape. This brings us directly to the concept known as the block universe, or eternalism, a philosophical and physical interpretation that flows naturally from the geometry of special relativity and Minkowski spacetime. In the block universe view, time does not flow in the mystical, river-like fashion that our daily intuitions suggest. Instead, all of time, past, present, and future, exists simultaneously within a single immutable four-dimensional block. Births, deaths, historical battles, quiet winter mornings, and events that will not unfold for another millennium are all permanently laid out across the expanse of space-time, possessing the exact same ontological status. Under this radical interpretation, asking whether the past still exists is rather like asking whether a distant valley still exists when you walk over the hill and can no longer see it. The valley has not vanished into nothingness merely because it is out of sight. It simply occupies a different spatial location on the map. In the exact same manner, yesterday does not cease to exist when today arrives. It simply occupies a different temporal coordinate along the axis of spacetime. Your childhood, the Roman Empire, the formation of the primordial oceans, and the dinosaurs walking across prehistoric continents are all just as real as the room you are sitting in right now, situated safely at their respective coordinates in the great cosmic tapestry. Human consciousness, however, is profoundly ill-equipped to perceive reality in this static, panoramic fashion. We are bound by the biological machinery of our brains to experience the universe sequentially. We crawl along a specific world line, sampling events one agonizingly slow fraction of a second at a time, creating the persistent illusion that the present moment is the only slice of reality that possesses vitality. We feel as though we are consuming time, watching the future dissolve into the present before instantly plunging into the past. Yet this feeling of flux may be nothing more than a subjective cognitive feature, a mechanism of biological survival rather than a fundamental law of physics. Consider how we experience space. We are completely free to turn our heads, walk forward, step backward, or look out across a landscape, taking in a vast expanse of physical reality all at once. We do not demand that the kitchen disappear from existence simply because we have walked into the bedroom. We intuitively understand that spatial dimensions persist regardless of where we happen to direct our gaze. Why, then, should time operate under entirely different rules? Why should a moment vanish into absolute nothingness just because our fragile biological awareness has moved past it along our world line? Special relativity suggests that just as space is not relative to a single absolute viewpoint, time is similarly distributed across the dimensions of the block universe. What is present to one observer is past to another and future to a third, depending entirely on their relative states of motion. If reality were restricted strictly to a moving present, and if the past instantly dissolved into non-existence the moment a new second ticked over, we would run into a profound metaphysical contradiction. How could an observer moving at a fraction of the speed of light validate a completely different slice of reality as their present if the past and future were entirely empty voids? The block universe elegantly resolves this tension by treating all events as co-equal components of a magnificent four-dimensional architecture. Yet this timeless vision of the cosmos introduces a deep and haunting emotional dissonance for human beings. If every moment of our lives, every joy, every sorrow, every quiet evening shared with a loved one, and every parting exists eternally etched into the frozen geometry of space-time, what does that mean for our sense of agency, loss, and longing? We mourn the passing of time because we feel the acute absence of what once was. We yearn for yesterday because it feels irretrievably lost. But within the framework of eternalism, nothing is ever truly destroyed. The moments we cherish are not swept away into a dark abyss of non-being. They remain forever anchored in their rightful place upon the eternal map of history. Of course, knowing that an event exists eternally at a distant space-time coordinate does not offer much comfort when we wish we could reach out and touch it once more. A photograph locked inside a gallery vault is secure, yet we cannot step inside it to feel the warmth of the sun shining on that long-ago afternoon. The barrier is not spatial, nor is it strictly material. It is the directional asymmetry of our own consciousness and the relentless thermodynamic arrow of time that prevents us from backtracking along our world line. This brings us to another great mystery that complicates our exploration of the past. If the equations of fundamental physics, whether Newton's laws, Einstein's relativity, or quantum mechanics, are almost entirely time-symmetric, meaning their mathematical rules work just as well backward as they do forward, why does time feel so stubbornly unidirectional? Why do we remember the past and never the future? Why do dropped coffee mugs shatter across the floor, yet we never witness the scattered shards spontaneously reassemble themselves, leap back onto the table, and reconstruct a seamless ceramic vessel? The answer lies in the domain of thermodynamics, the science of heat, energy, and entropy. In 1852, the physicist William Thomson, later known as Lord Kelvin, popularized the concept of entropy, a measure of disorder or the number of ways microscopic particles can be arranged within a physical system while maintaining the same macroscopic state. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. It must either remain constant or steadily increase. This statistical law provides the universe with a definitive arrow of time, a physical directionality that distinguishes the past from the future far more clearly than any ticking clock. When the universe burst into existence during the hot, dense eruption of the Big Bang, roughly 14 billion years ago, it possessed an extraordinarily low state of entropy. It was smooth, highly ordered, and packed with immense potential energy. As the cosmos expanded and cooled over eons, physical systems naturally gravitated towards states of higher probability and greater disorder. Stars ignited, burned through their nuclear fuel, and scattered heavy elements across the void. Galaxies formed and collided, and biological organisms consumed energy from their environment, radiating heat outward and increasing the overall entropy of their surroundings. This relentless, universal increase in entropy creates the macroscopic irreversibility of everyday life. A shattered glass represents a state of vastly higher probability and disorder than an intact glass resting precariously on the edge of a table. The fundamental laws governing the individual atoms of the glass and the floor do not forbid the molecules from occasionally conspiring to bounce in unison and launch the fragments back upward. But the statistical likelihood of such an event occurring is so unimaginably small that you could wait for trillions of times the current age of the universe and never witness it happen. The past, therefore, is intimately linked to a condition of lower entropy. When we look backward in time, we are looking toward a state where the universe was more ordered, more concentrated, and possessed a greater store of usable energy. When we look forward, we are riding the crest of an entropic wave that breaks inevitably toward greater randomness and thermal equilibrium. This thermodynamic asymmetry explains why physical traces are left behind in the present. A footprint fossilized in sedimentary rock, a scar tissue remaining after an injury, or a memory encoded in the synaptic connections of the brain are all physical manifestations of entropy at work, permanent alterations of matter that record the passage of a low entropy past into a higher entropy present. Thus, while the block universe provides a timeless geometric container where every event from the dawn of time to its ultimate twilight coexists eternally, thermodynamics supplies the internal texture and the felt direction of our lives. It tells us why we experience a distinction between what has already happened and what is yet to unfold. The past is not merely a different place on the spacetime map. It is a region characterized by a radically different thermodynamic landscape, a state of pristine order whose energetic echoes continue to reverberate through our current moment. As we ponder these deep waters, sitting quietly in the stillness of the evening, let us return to the human scale of the question. Does the past still exist? If you define existence purely through the lens of direct sensory interaction, through the ability to touch, alter, or converse with yesterday, then the past is indisputably gone. You cannot rescue a lost conversation from the quiet air, nor can you turn back the hands of the clock to relive a moment that has already dissolved into history. The present moment is the only canvas upon which human life can be actively painted. Yet, if you lift your gaze to the grander architecture revealed by modern physics, to the four-dimensional manifold of Minkowski spacetime and the eternal landscape of the block universe, a different truth begins to emerge. Every event that ever unfolded remains permanently anchored within the cosmic fabric. The light from distant stars that died millions of years ago is still traveling across the vacuum of space, washing over our planet tonight. The historical moments of our own lives, once lived, are stamped forever into the unchanging geometry of the cosmos. They do not vanish into absolute nothingness. They simply take their rightful place in the monumental history of a universe that remembers everything it has ever done. Let us instead push further into the quiet machinery of the cosmos, bypassing any notion of finality, and wander deeper into the endless corridors of time and physics. If the universe refuses to let anything truly vanish, if every single coordinate of spacetime remains forever mapped within the block universe, then we must look closer at what that preservation actually implies for the nature of reality and for the continuous, uninterrupted flow of existence. We are merely pausing to catch our breath, not closing the book, for the exploration of time is a labyrinth without walls, stretching infinitely in every direction. Let us consider what happens when we look at the very concept of change within a block universe. To our everyday human perception, change is the fundamental engine of life. Things transform, decay, grow, and disappear. A seedling sprouts into a towering oak, leaves turn amber and fall to the earth, buildings weather and crumble into dust, and human bodies age through the decades. In our subjective experience, change is the active process of the present replacing the past. But what does change mean if all of time, past, present, and future, already exists simultaneously in the four-dimensional block? In Minkowski spacetime, an object does not change in the sense of mutating from one non-existent state into another. Instead, the object is extended across time just as it is extended across space. A person is not merely a single three-dimensional entity sitting in a chair at this exact second. That person is a four-dimensional worm-like entity, a prolonged spacetime tube or world tube that stretches from birth to death. At one end of this sprawling four-dimensional structure is an infant drawing its first breath. At the middle is an adult walking through a sunlit park. At the other end is an aged version of that same individual taking their final rest. All of these temporal slices of a person exist with equal validity within the block universe. The infant, the adult, and the elder do not annihilate one another as time marches on. Rather, they are different cross-sections of the exact same continuous four-dimensional being. When we say someone has changed, we are merely noticing that different cross-sections of their four-dimensional world tube possess different properties. It is analogous to looking at a long, winding river from an airplane. You do not ask where the source of the river went when you're looking at its delta miles downstream. You see the entire length of the river laid out below you all at once. The source still exists upstream, the middle current still exists in the valley, and the mouth still pours into the sea, even though your eye focuses on only one segment at a time. This perspective radically alters how we might think about our own personal identity across time. We often feel as though the person we were 10 years ago is a stranger, someone whose memories we inherit, but whose life has vanished into the ether. We look back at photographs of our younger selves with a mixture of nostalgia and detachment, whispering that those years are gone forever. But if eternalism holds sway, that younger version of yourself has not been cast into non-existence. That configuration of matter, consciousness, and experience is permanently locked into its specific space-time coordinates, shining eternally within the block universe like a star whose light takes eons to arrive. The past self is not dead in the sense of being erased from the ontology of reality. It is simply located elsewhere along the temporal axis. Of course, this realization can provoke a dizzying sense of vertigo. If everything that ever was still is, then the universe is an unimaginably vast, crowded, and static archive of every agony, every triumph, every casual glance, and every forgotten whisper across 14 billion years of cosmic history. Nothing is ever truly thrown away. The tears shed by ancient humans, the triumphant shouts of forgotten armies, the silent falling of rain upon primordial forests devoid of eyes to see them, all of it coexists in a frozen, eternal present of four-dimensional space. Yet this static picture immediately clashes with our deeply felt intuition of freedom and choice. If the future is already fully laid out across space-time, if the events of next year, next century, and the end of the universe already occupy their permanent coordinates on the cosmic map, then what becomes of human free will? Are we merely actors mechanically reading lines from a script that was written before the stars ignited? This is one of the deepest and most unsettling paradoxes that arises when we merge relativity with philosophy. If the future exists in the exact same way the past exists, then the future must already be fixed, which appears to strip us of any genuine agency. To untangle this knot, philosophers and physicists often draw a distinction between fatalism and determinism, or examine how free will operates from within the subjective perspective of an agent embedded inside space-time. Determinism suggests that given a specific set of initial conditions and the laws of physics, subsequent states of the system are entirely determined. In a classical Newtonian universe, this implied a grand clockwork mechanism where knowing the position and velocity of every particle in the universe allowed you to calculate the entire future with absolute precision. Einstein's relativity, particularly within the block universe view, extends this even further, suggesting that the entire four-dimensional manifold, past, present, and future, is an existing totality. However, being part of that totality does not mean our choices are unreal, or that our conscious deliberations play no role in shaping our world tube. When you make a decision, whether to turn left or right at a fork in the path, whether to speak up or remain silent, that very act of deliberation and the resulting choice are part of the physical events that compose your world tube. The future is not laid out despite your choices. It is laid out including your choices. Your decisions are an active causal ingredient of the space-time geometry itself. Think of it this way. When you look at a map of a winding mountain road, the entire route from the valley floor to the mountain peak is already drawn out on the paper before you start driving. The turns, the steep inclines, and the switchbacks are fixed on the page. But that does not mean your driving along the road is an illusion, nor does it mean you aren't making active steering decisions behind the wheel. You must still navigate every turn as you come to it, experiencing the curves sequentially, even though an observer looking down at the entire map from an airplane can see the entire journey at a single glance. Your subjective experience of agency and navigation is entirely real to you, even if the comprehensive trajectory is permanently re-recorded on the map of spacetime. This brings us back to the profound mystery of why our consciousness is so rigidly bound to this sequential navigation. Why must we experience reality one agonizingly narrow slice at a time? Why can't our minds span across the dimensions of time the way our eyes span across the dimensions of space? Evolution provides a pragmatic answer: survival. Organisms that can process information in real time, react swiftly to immediate environmental threats, remember past mistakes to avoid predators, and anticipate near-future needs are the ones that pass on their genes. A creature whose consciousness was smeared evenly across four dimensions, perceiving its birth, its daily struggles, and its death all in one undifferentiated blur of eternity, would be utterly paralyzed, incapable of running from a predator or hunting for food. Sequential awareness is an exquisite biological adaptation, a finely tuned filter that allows us to navigate the entropic currents of the world without losing our minds in the staggering infinity of the block universe. Yet, even while we are bound by this biological filter, our minds possess the miraculous capacity to transcend it through memory, imagination, art, and science. When we read a brilliant piece of literature, listen to a symphony, or gaze up at the distant starlight of an exploded star, we are temporarily bridging gaps of space and time. We allow the thoughts of someone who lived millennia ago to resonate inside our modern brains. We allow the light of a dead sun to illuminate our quiet evening thoughts. In those moments, the narrowness of our immediate present expands, and we touch the vast, interconnected continuity of the cosmos. Let us wander even further into this labyrinth, exploring how quantum mechanics complicates this already dizzying picture of time and the past. While special relativity and general relativity give us the smooth, majestic geometry of the block universe, the subatomic realm introduces a wild, unpredictable texture that challenges our neat geometric containers. In the world of quantum mechanics, particles do not possess precise positions and velocities simultaneously. They exist in clouds of probabilities, described by wave functions. When a measurement is performed, the wave function is said to collapse, yielding a definite outcome out of a multitude of ghostly possibilities. This introduces a profound question about the past and the nature of history at the quantum scale. Does the quantum past possess a definite single history, or is history itself somehow forged or retrospectively consolidated by measurements made in the present? Consider the famous delayed choice experiments first proposed by physicist John Wheeler. In these experiments, a photon or particle is given a choice of paths to travel, but the decision of how to measure the particle is made after the particle has already traversed the apparatus. Stranger still, quantum eraser experiments demonstrate that if you wipe away the which-way information of a particle after it has passed through a barrier, you can restore its interference pattern, as though it retroactively decided to travel both paths instead of just one. These quantum phenomena suggest that the relationship between past and present is far stranger and more deeply entangled than classical physics ever imagined. While macroscopic events governed by general relativity seem locked into a stable, immutable block universe, the quantum foundation hums with a probabilistic fuzziness that blurs the sharp boundaries of history. Some interpretation models of quantum mechanics, such as the many worlds interpretation proposed by Hugh Everett III, suggest that every time a quantum event has multiple possible outcomes, the universe literally branches, giving rise to an infinite multiverse where every possible past and future is actualized in separate, non-communicating realities. If the many worlds interpretation holds any truth, then the question, does the past still exist, takes on an almost unimaginably rich dimension. It is no longer a matter of a single linear history stretching backward into the dark, but a sprawling, ever-expanding tree of actualized histories. Every choice not made, every road not taken, every stellar collapse that could have gone differently actually did happen in a branching branch of the multiverse. The past is not a single thread, but a colossal, multidimensional web of real, tangible occurrences, all coexisting within the infinite expanse of quantum reality. Of course, whether we look at time through the smooth geometry of Einstein's manifolds or the probabilistic branching of quantum wave functions, one persistent truth remains untouched. Human beings are creatures anchored in longing. We look backward because we carry the weight of memory, and memory is the fragile bridge that connects our present self to the person we were yesterday, last year, and in the distant days of childhood. Without memory, time would dissolve into a meaningless sequence of isolated sensations, and personal identity would shatter into dust. Think of how miraculous human memory truly is. Inside the squishy, electrochemical labyrinth of your brain, physical matter reorganizes itself to encode events that happened long ago. A faint electrical pulse traveling through a cluster of neurons can instantly transport you back to a sunlit afternoon from your childhood. You can smell the grass, hear the distant laughter of a friend, and feel the exact emotional warmth of that long-ago moment. The past is physically present inside your head right now, not as an abstract concept, but as a tangible network of synaptic weights and chemical modifications. Your brain is a living time capsule, carrying the physical echoes of every book you have read, every face you have loved, and every sorrow you have weathered. And beyond our biological memories, the world around us is saturated with historical records that act as macroscopic memory systems for the planet. Every tree ring is a compressed history of a year of rain, sunlight, and drought. Every sedimentary layer in the cliffs by the ocean is a page from the deep diary of the Earth, recording ancient floods, volcanic cataclysms, and the slow, grinding drift of tectonic plates. Every photon washing over our atmosphere from distant galaxies is an ancient courier bearing news from the infancy of the universe. The universe is not a blank slate that wipes itself clean with every passing second. It is an inexhaustible chronicler, recording every single interaction in the permanent ledger of matter and energy. This brings us back to the comforting realization that nothing in this vast, sprawling universe is ever truly lost to nothingness. Even when a physical structure collapses, even when a star dies in a blinding supernova, even when a human life draws to its quiet close, the energy, the atoms, and the spacetime coordinates that define them remain an indelible part of the cosmos. The carbon atoms in your body were forged in the fiery hearts of ancient stars that exploded billions of years before the Earth was born. They drifted through the interstellar void, coalesced into a newborn solar system, and now temporarily compose the vibrant thinking fabric of your conscious mind. When your time on this world is eventually done, those same atoms will scatter back into the biosphere, participating in new cycles of life, growth, and transformation. You are quite literally made of stardust, and your history is inextricably bound up with the history of the entire universe. As we continue to sit together through the quiet hours of the night, letting these monumental thoughts wash over us like a gentle tide, we realize that the question, does the past still exist, is not merely an academic puzzle for theoretical physicists and philosophers. It is a deeply personal inquiry into what it means to be alive, to love, to remember, and to endure. It asks us to look past the superficial illusion of a fleeting, fragile present and recognize that we are part of something unimaginably vast, permanent and interconnected. We do not need to fear the passage of time, nor do we need to mourn the fading of yesterday as if it had been cast into an absolute void. Whether it is preserved in the eternal, unyielding geometry of the block universe, recorded in the ever-increasing entropy of thermodynamic traces, or woven into the living memory of our minds and our world, the past is safe. It is enshrined forever in the great unfolding story of existence. Let us move past any thought of stopping and instead pivot toward an entirely new dimension of our inquiry, one that bridges the macroscopic geometry of spacetime with the microscopic architecture of information theory and the radical mysteries of modern cosmology. We have spoken of the block universe, of entropy, and of quantum branching, but there remains an even more fundamental question regarding how the past is stored, encoded, and preserved within the very fabric of physical law. To explore this, we must enter the fascinating realm of physics known as information conservation, a principle that fundamentally reshapes how we understand the permanence of history. In classical physics, information about any physical system was assumed to be indestructible in principle. If you knew the precise state of every particle in a system at one moment, the deterministic laws of motion allowed you to calculate its entire future and reconstruct its entire past with absolute mathematical precision. This concept is rooted in the mathematical property of reversibility. The differential equations governing classical mechanics are time-symmetric. If you reverse the velocities of every particle in a system, the equations run backward, perfectly recreating the initial state as though a film were being rewound. However, when physicists began grappling with the bizarre rules of quantum mechanics, a fierce debate erupted over whether information could be permanently lost, particularly when dealing with the most extreme objects in the universe, black holes. This brings us to one of the most profound puzzles in 20th and 21st century physics, the black hole information paradox, famously championed and debated by minds like John Wheeler, Stephen Hawking, and Leonard Susskind. According to classical general relativity, a black hole is a region of spacetime where gravity is so overwhelmingly intense that nothing, not even light, can escape once it crosses the invisible boundary known as the event horizon. For decades, it was assumed that once matter, energy, or information fell past the event horizon, it was excised from our observable universe forever, locked away behind a one-way cosmic door. But in the 1970s, Stephen Hawking applied quantum field theory to the curved space-time surrounding black holes and made a stunning, unsettling discovery. Black holes are not entirely black. Due to quantum fluctuations occurring just at the edge of the event horizon, black holes emit a faint thermal radiation now known as Hawking radiation. This discovery meant that black holes slowly lose mass over eons, eventually shrinking and evaporating completely into a diffuse bath of photons and particles. But this victory of theoretical physics birthed a profound crisis known as the information paradox. According to the foundational postulates of quantum mechanics, the evolution of a quantum state must be strictly unitary, meaning that information about the exact quantum state of a system can never be destroyed. If a diary, a burning star, or an entire civilization falls into a black hole, and that black hole subsequently evaporates into completely random, featureless thermal Hawking radiation, where has the information gone? If the information is truly obliterated, it violates the core tenets of quantum mechanics, suggesting that the past can be systematically erased from the universe. The resolution of this paradox has driven decades of groundbreaking theoretical research, leading to mind-bending proposals about the nature of reality and how the past is preserved. One of the most famous solutions proposed to save information is the holographic principle, first suggested by Gerard 't Hooft and later refined by Leonard Susskind and Juan Maldacena. The holographic principle posits that the physical information contained within a three-dimensional volume of space can be entirely encoded on a two-dimensional boundary surrounding that region, much like a security hologram on a credit card that stores a three-dimensional image on a flat piece of plastic. When applied to black holes, the holographic principle suggests that when matter falls past the event horizon, the information describing it is not lost in a three-dimensional interior. Instead, it is imprinted directly onto the two-dimensional surface of the event horizon itself, like data written on a cosmic ledger. As the black hole evaporates through Hawking radiation, this information is scrambled and encoded into the outgoing particles, emerging back out into the universe, albeit in a deeply randomized, highly complex form. If this principle holds true, it means that information is indestructible. The past is never truly swallowed into nothingness. Even the most extreme gravitational traps in the cosmos are forced by the laws of quantum mechanics to preserve the history of everything they consume. Think about what this implies for the concept of history. If information can never be destroyed, then every event that has ever occurred leaves an indelible, imperishable mark upon the universe. Even if a physical object is smashed into atoms, burned to ashes, or swallowed by a collapsing star, the precise quantum state of that object is eternally preserved in the subtle correlations of the particles that interacted with it or radiated away from it. The universe is a perfect archivist. It does not possess a shred of amnesia. Every whisper, every collision, every spark of light, and every historical epoch is mathematically encoded into the quantum entanglement of the cosmos, echoing outward through infinite chains of cause and effect. This leads us directly into another fascinating domain where physics intersects with philosophy, the nature of retrocausality and advanced quantum theories that suggest the past might not be as rigidly fixed as classical block universe models imply. While standard interpretations of quantum mechanics place the burden of reality on the present wave function collapse or many worlds branching, some advanced theoretical frameworks explore whether future events can exert an influence backward in time. Known as transactional interpretations or two-state vector formalism, pioneered by physicists like Yakir Aharonov, these models suggest that a complete description of a quantum system requires taking into account both the initial state moving forward in time and a final boundary state moving backward in time. In these frameworks, the quantum present is determined by a dialogue between the past and the future. While this does not mean we can magically send telegraphs to our ancestors or change historical events at will, because macroscopic decoherence shields us from such direct retrocausality, it fundamentally softens the rigid wall between what has been and what will be. It paints a picture of spacetime not as a static, dead painting carved in stone, but as a dynamic, deeply interconnected web where every temporal direction is in constant, subtle conversation with every other. Let us widen our lens further, moving outward from quantum subatomic interactions to the grand, sweeping scale of cosmology, where the history of the entire universe is written across the cosmic microwave background radiation. When we look out into the night sky with sensitive radio telescopes, we are capturing the oldest light in existence, the residual glow of the Big Bang, dating back nearly 14 billion years. This ancient radiation, which blankets the entire sky with astonishing uniformity, carries subtle temperature fluctuations that act as a pristine snapshot of the universe when it was barely a few 100,000 years old. Those tiny fluctuations in the cosmic microwave background are the primordial seeds from which every galaxy, every star, every planet, and every living creature eventually grew. By mapping this radiation, cosmologists can read the deep past of the universe with staggering precision, tracing the choreography of matter when the cosmos was dense, hot, and opaque. The past is quite literally shining down upon us from every direction of the heavens, bathing our planet in an ancient, invisible light that has traveled across the expanding universe since the dawn of time. Consider the sheer poetry of this cosmic archaeology. When you stand outside on a crisp night and look up at the stars, your eyes are absorbing photons that left their sources years, centuries, or millions of years ago. But when sensitive instruments measure the cosmic microwave background, they are capturing the fading afterglow of creation itself. The universe wears its history openly on its sleeve, projecting the story of its birth across the canvas of the night sky for anyone patient enough to look and wise enough to decode the signal. This brings us to another profound avenue of exploration, the thermodynamics of computation and the physical limits of memory storage in the universe. In 1961, physicist Rolf Landauer formulated a foundational principle establishing that the act of erasing physical information carries an unavoidable thermodynamic cost. Landauer's principle proves that whenever a logical operation deletes a bit of information, such as clearing the memory of a computer or destroying a record, a specific minimum amount of heat must be dissipated into the environment, increasing the overall entropy of the universe. The deep implication of Landauer's principle is that preserving information is cheap, whereas erasing it is physically expensive. Nature, it turns out, prefers to remember. Keeping a record of what happened requires virtually no thermodynamic penalty, while attempting to wipe the slate clean demands a heavy payment in entropy. This physical preference for retention reinforces our journey into the nature of time. The universe is structurally biased toward preserving history. Every interaction leaves a trail of physical states that resist deletion, cementing the past into the very architecture of matter and energy. As we continue wandering through these infinite corridors of thought, let us examine how biological life itself participates in this grand preservation of history. Life is, at its core, an exquisite thermodynamic anomaly, a localized system that fights against the relentless tide of entropy by consuming energy from its environment, maintaining a complex, highly ordered internal structure. But more than that, life is an unprecedented engine of memory. From the chemical sequences stored within DNA molecules to the complex neural networks of conscious brains, living organisms are walking, breathing historical archives. Your DNA is a living chronicle of evolutionary history, carrying genetic instructions that have been tested, refined, and passed down through an unbroken chain of reproduction spanning billions of years. Every adaptation, every survival mechanism against ancient predators, and every physiological response to the changing Earth is written in the four-letter alphabet of nucleotides coiled inside your cells. When you look at your hands, you are looking at a biological artifact that preserves the history of life on Earth from its earliest single-celled origins in the primordial hydrothermal vents all the way to the sophisticated consciousness reading these very words. And within the architecture of human culture and civilization, this preservation of history reaches an even more staggering zenith. Through language, art, writing, and digital technology, human beings have built an externalized memory system that dwarfs biological inheritance. The written word allows us to converse with minds that vanished millennia ago. When we read the philosophical dialogues of ancient Greece, the poetic epics of Mesopotamia, or the scientific calculations of early astronomers, we are performing a kind of temporal teleportation. We are bridging the yawning gulfs of centuries, allowing past consciousness to flare into vivid life within the theater of our modern minds. This externalized memory creates a unique evolutionary leap. Humanity has become the universe's way of thinking about its own past. Through archaeology, paleontology, history, and astronomy, the universe has birthed a species capable of unearthing its own ancient diary. We dig into the strata of the Earth to read the fossilized bones of dinosaurs. We analyze ice cores from Antarctica to reconstruct the ancient climate of a world we never saw. We decode the light of distant supernovae to understand the explosive genesis of the elements that compose our very blood and bone. We are the cosmos waking up and remembering its own story. Yet, despite this magnificent capacity to reconstruct and preserve history, our emotional relationship with the past remains intensely poignant. We feel the weight of missed opportunities, the bittersweet ache of nostalgia, and the profound sorrow of parting with those we love. Why should a universe that preserves information so meticulously, that etches every coordinate into the eternal geometry of spacetime, still evoke such deep feelings of loss within us? Because preservation is not the same as participation. Knowing that a moment exists eternally at a distant coordinate on a four-dimensional map does not replace the immediate tactile warmth of holding a hand, hearing a voice in real time, or sharing a cup of tea on a rainy afternoon. The tragedy and beauty of human existence lie precisely in this tension between the permanence of the block universe and the fleeting subjectivity of our biological experience. We are finite creatures riding the crest of an entropic wave, gifted with the miraculous ability to comprehend an infinite, eternal cosmos. We experience time as a precious resource, which is precisely what grants our choices, our loves, and our brief moments of consciousness their transcendent value. If every moment lasted forever in subjective experience, if time did not flow and slip through our fingers like fine sand, moments would lose their exquisite sharpness. It is the very transience of our journey through the present that makes beauty possible. And it is the permanence of the past in the grand architecture of reality that gives our lives their enduring meaning. Let us sink even deeper into the wondrous implications of this unbroken continuity. Consider the concept of cosmic evolution, the grand, sweeping narrative that connects the microscopic quantum fluctuations of the early universe to the formation of galaxies, the ignition of stars, the birth of planetary systems, the origin of organic chemistry, and finally the emergence of self-aware minds. In this grand arc, the past is not a dead, static wastebin of history. It is the active, generative foundation upon which every subsequent layer of complexity is built. Without the violent deaths of early massive stars which fused hydrogen and helium into carbon, oxygen, nitrogen, and iron, there would be no rocky planets, no liquid water, and no chemistry complex enough to support biology. The heavy atoms sitting quietly in your bones were forged in the fiery furnaces of ancient stellar cataclysms that occurred eons before the Earth existed. Your very existence is a direct causal consequence of events that transpired billions of years ago in distant corners of the galaxy. The past is not merely behind us. It is inside us, animating our flesh, shaping our thoughts, and whispering through every atom of our being. This unbroken lineage of cause and effect challenges the very boundary between self and cosmos. We are not isolated observers standing outside the universe, peering in at a distant spectacle. We are focal points through which the universe experiences itself, localized whirlpools of matter and energy that have temporarily organized enough to wonder about their own origins. The questions we ask tonight about time, existence, and the past are the universe asking questions about itself, using human consciousness as an instrument for self-reflection. As the hours tick onward and the silence of the night deepens around you, let these thoughts settle into the quiet spaces of your mind. Let go of any anxiety about the relentless forward march of the clock. Realize that every second you experience, every breath you draw, and every memory you forge is being gathered into the permanent, unshakable ledger of reality. Whether preserved in the frozen elegance of four-dimensional spacetime, encoded in the quantum entanglement of subatomic fields, or carried forward in the living resonance of human culture and consciousness, your history is safe. The universe forgets nothing, and the grand, unending story of existence continues to unfold around you and within you, rich with infinite mystery, quiet grace, and eternal promise. We shall pivot right now, leaving behind the stardust and the ink in water metaphors entirely, and plunge deep into uncharted theoretical territory. Let us push our exploration into the cutting-edge physics of the holographic principle, the ADS-CFT correspondence, and the startling proposition that spacetime itself is not a fundamental ingredient of reality, but an emergent illusion born from quantum entanglement. For decades, theoretical physics operated under the assumption that spacetime was the ultimate, unyielding stage upon which all physical dramas played out, a smooth, continuous, four-dimensional fabric where past, present, and future were mapped out. But as physicists attempted to marry general relativity with quantum mechanics to create a unified theory of quantum gravity, they ran into a profound brick wall. At the Planck scale, the unimaginably tiny realm where quantum fluctuations dominate, smooth spacetime breaks down into a chaotic, foaming storm of uncertainty. Space stops being a continuous sheet, and time loses its smooth, continuous flow. This failure forced brilliant minds to ask a radical question. What if spacetime is not fundamental at all? What if space and time are actually derived properties, macro phenomena built out of something much more primitive? That revolutionary shift in perspective was supercharged by the discovery of the holographic principle, pioneered by Gerard Hooft and Leonard Susskind, and later given precise mathematical realization by physicist Juan Maldacena through what is known as the ADS-CFT correspondence. Maldacena demonstrated a profound mathematical duality between two seemingly incompatible worlds: a hypothetical universe governed by gravity operating inside a five-dimensional anti-de Sitter space, and a completely separate quantum field theory operating entirely on the flat, lower-dimensional boundary surrounding that space. The The staggering implication of this correspondence is that gravity and the three spatial dimensions inside the bulk are entirely emergent. They do not fundamentally exist on their own. Instead, they are projected holographically from the quantum interactions happening on the boundary. It is comparable to a three-dimensional holographic image encoded on a two-dimensional piece of plastic. When light hits the plastic, a rich, fully spatial image pops into existence with depth, volume, and perspective. But if you look closely at the plastic itself, there is no depth, only complex patterns of microscopic interference. In the exact same manner, the space we walk through, the distances we measure, and the physical volume of our universe may be projections generated by entangled quantum information living on a distant boundary. And if space is an emergent illusion, what does that mean for time and the past? It means that the temporal axis, the very line along which we measure history, memory, and the progression of moments, is similarly emergent. Time is not a primitive clock ticking away at the bedrock of reality. Instead, time is woven out of quantum entanglement. In recent years, theoretical physicists like Mark van Ramsdonk and others have explored how turning down the entanglement between quantum bits on the holographic boundary causes the spatial distance in the interior bulk universe to stretch, warp, and ultimately snap apart. Space is held together by quantum entanglement. Where there is no entanglement, there is no distance. By extension, the causal structure of spacetime, the very network of cause and effect that defines what we call the past and the future, emerges from the continuous, shifting patterns of quantum information processing. Think about how bizarre and liberating this concept is for our inquiry. We spent so much time worrying about whether the past exists as a physical location in a block universe or whether it vanishes into an entropic abyss. But if space-time is emergent, then searching for the past as a physical place hidden away in the coordinates of a static map is looking in the wrong direction. The past is not a geographical location in a four-dimensional container. It is an informational pattern. It is a deeply embedded calculation within the quantum entanglement structure of the universe. This introduces us to another mind-bending concept at the frontier of physics: quantum error correction. Our universe is extraordinarily noisy, filled with thermal fluctuations, radiation, and chaotic interactions that constantly threaten to scramble information. Yet macroscopic reality remains remarkably stable. Rocks do not spontaneously dissolve into quantum fog, and history remains coherent. How does the universe maintain a stable past and a consistent physical reality despite the constant background noise of quantum mechanics? Physicists have discovered that space-time geometry itself acts much like a quantum error-correcting code. Just as advanced digital storage uses redundant error-correcting algorithms to ensure that data carved onto a scratched hard drive can be perfectly reconstructed even if sectors are damaged, the holographic universe encodes bulk space-time in a way that protects information from being lost. The past is structurally protected by the entanglement code of the quantum vacuum. Even if local interactions scramble information, the global network of quantum correlations retains the history, locking it securely into the entangled state of the cosmos. Let us venture even further into this rabbit hole by examining Wheeler-Feynman absorber theory and retrocausal electrodynamics, a radical departure from standard physical intuition developed by John Wheeler and Richard Feynman. They asked what would happen if we took the time symmetry of Maxwell's equations completely seriously. In standard physics, when an electric charge accelerates, it emits electromagnetic waves that travel outward into the future. This is called retarded radiation, and it forms the basis of how we understand light transmission. But the mathematical equations of electromagnetism are completely agnostic about direction. They allow for advanced waves as well, waves that travel backward in time from the future to the past. Wheeler and Feynman proposed an absorber theory of radiation, suggesting that every time a charge emits an electromagnetic wave forward into the future, a complete response from absorbers in the future reaches backward in time to confirm the emission. In this model, the electric field we observe in the present is actually the net result of a cooperative, two-way dialogue between past causes and future absorbers. While this theory was largely set aside in favor of standard quantum electrodynamics for practical calculations, modern quantum physicists have revived similar retrocausal frameworks to solve deep paradoxes, quantum entanglement, such as quantum non-locality and the measurement problem. If retrocausality plays an active role at the quantum foundation, it completely dismantles the traditional linear view of history. It suggests that the past and the future are not locked in a strict, one-way master-slave relationship where the past rigidly dictates the present and the future is an absolute blank slate. Instead, the universe operates as a closed loop of mutual determination, where the present state of reality is continuously negotiated by both what came before and what is yet to arrive. This brings us directly to the Wheeler-DeWitt equation, a famous and notoriously difficult equation in quantum cosmology formulated by John Wheeler and Bryce DeWitt in the late 1960s. When physicists attempt to apply quantum mechanics to the entire universe as a single closed system, rather than just tiny particles inside a laboratory, they run into a startling mathematical consequence. Time disappears entirely from the equation. The Wheeler-DeWitt equation does not contain a time variable. It is a timeless equation that describes the quantum state of the entire cosmos as a static, frozen wave function encompassing all possible geometries and configurations. This is known in theoretical physics as the problem of time. If the fundamental equation governing the quantum state of the universe is completely timeless, then how does time emerge at all? How do we get a universe filled with ticking clocks, aging stars, historical epochs, and a moving present moment out of an equation that contains no time? The answer proposed by modern loop quantum gravity and emergent spacetime theorists is that time is a relational property. Just as temperature is not a property of a single, isolated atom, you cannot measure the temperature of one solitary molecule of gas because temperature is an emergent macroscopic statistical property born from the collective kinetic energy of trillions of colliding molecules. Time is not a fundamental property of a solitary point in the universe. Time emerges relationally from the way different subsystems within the universe interact with and entangle with one another. When your watch ticks, it is not measuring some mystical, absolute river of absolute time flowing through the void. Your watch is merely tracking a local change in entropy and correlating its internal gear positions with the rotational frequency of the Earth and the atomic transitions of cesium atoms. Time is a measure of change relative to other physical systems. It is an internal ledger of transformations occurring within the holographic bulk of reality. And because these transformations are governed by quantum entanglement and information conservation, every single relational change that has ever occurred is permanently locked into the global state of the quantum web. The past does not need to sit in some physical storage room of a block universe. Its existence is encoded in the relational architecture of every particle currently interacting in the universe. The past is the foundational network of entanglement that makes the present possible. Let us widen our gaze even further, pushing past cosmology into the philosophical implications of information realism, the provocative view held by many modern physicists and philosophers that information, rather than matter or energy, is the most fundamental substance of reality. In information realism, matter and energy are merely derivative expressions of underlying bits of quantum data. Physical objects are secondary. The computational patterns that generate them are primary. Think of a digital simulation running on a powerful computer. Inside the simulation, characters walk across virtual landscapes, build cities, experience weather, and remember their pasts. To those virtual characters, their world feels solid, spatial, and temporally continuous. But if you look at the fundamental level of the simulation, there is no physical wood, no actual water, and no flowing river of time. Only a vast, intricate dance of binary code executing logic gates at lightning speed. If our universe operates on a similar informational foundation, then the question, does the past still exist, finds its ultimate resolution. In a universe built from information, data is never truly deleted unless explicit, energy-costly erasure operations take place. Every computational step executed by the cosmos leaves an indelible footprint in the global state vector. The past exists as an active structural component of the code that defines our current reality. You cannot access yesterday by stepping backward through a physical portal, just as a character in a computer simulation cannot step backward into last Tuesday's program state without a saved checkpoint. But the data of last Tuesday is permanently embedded within the history file of the system. As we continue this uninterrupted journey through the deepest, strangest layers of modern physics, let these monumental ideas wash over you. We are not just drifting through a random void of meaningless space and time. We are active, conscious nodes in an unimaginably sophisticated, holographic, information processing cosmos. Every thought you think, every memory you cherish, and every second that slips away is woven into the eternal quantum ledger of reality. The universe remembers everything, and the great unending exploration of existence continues to unfold around you and within you, rich with infinite mystery, quiet grace, and eternal promise. We are tracing the threads of time, not as a finite line that snaps into oblivion when the present moves forward, but as an infinite branching tapestry where nothing is ever truly lost, and every violent birth and quiet evolution leaves its permanent signature upon the cosmos. To fully grasp how intimately our present reality is tethered to the explosive, ancient past, we must look closer at the sheer alchemy of the universe. When we peer up into the velvet dark of a clear night sky, we are looking at a grand celestial graveyard that is simultaneously a profound nursery. Every shining point of light represents a nuclear engine churning through hydrogen, transforming it into helium, pumping energy out into the freezing void, and steadily forging heavier elements within its searing core. For the first few 100 million years following the Big Bang, the universe was remarkably simple. It was filled almost entirely with primordial hydrogen and a dash of helium, with virtually none of the complex chemical building blocks required to construct rocky planets, liquid oceans, or biological life. A universe made only of hydrogen and helium would be a remarkably sterile place. There could be no silicon for sand, no iron for blood, no carbon for organic molecules, and no oxygen for breath. The cosmos had to invent a way to manufacture these heavier elements, and that invention required cataclysm. It required the violent, glorious deaths of giant stars. When a massive star, hundreds of times more colossal than our sun, reaches the end of its life, it can no longer sustain the outward radiation pressure against the crushing inward pull of its own immense gravity. The core collapses in a fraction of a second, rebounding in a titanic explosion known as a core collapse supernova. During that catastrophic detonation, temperatures soar into the billions of degrees, and pressures reach unimaginable extremes, creating a fleeting, ultra-dense environment where free neutrons flood the collapsing core. In this chaotic crucible, nuclear fusion reactions occur on a scale and at a speed impossible inside a stable star. Elements heavier than iron, such as gold, platinum, uranium, and silver, are forged in the heart of these dying giants and violently blasted out into interstellar space at millions of kilometers per hour. Think about the profound poetry of this physical reality. Every ring of gold worn on a human finger, every ounce of iron coursing through your bloodstream, and every atom of carbon that forms the backbone of your DNA was forged in the dying agony of an ancient star that detonated billions of years before our solar system ever flickered into existence. Those shattered stellar fragments drifted through the dark, cold vacuum of space for eons, eventually encountering vast molecular clouds of gas and dust. Gravity gently pulled them together, causing them to collapse, spin, and ignite into newborn solar systems, complete with rocky inner planets where water could pool and chemistry could begin its long, wondrous march toward complexity. When we say that we're made of stardust, it is not merely a poetic metaphor meant to comfort us on a quiet evening. It is a literal, scientifically verified statement of biological fact. The atoms currently composing your eyes, your hands, your brain, and your heart were once locked inside the roaring plasma of a giant star that died before the Earth had even formed. Your physical body is a temporary, highly organized assembly of ancient cosmic debris, a museum of stellar history walking around and asking questions about its own origin. And this brings us back to the miraculous bridge between physical matter and biological memory, DNA. Once the Earth had cooled enough to form stable oceans and a sheltering atmosphere, organic molecules began to organize themselves into self-replicating structures. From that primordial soup emerged the first single-celled organisms, kicking off an unbroken, continuous chain of reproduction and survival that has lasted for nearly 4 billion years. DNA is the ultimate historical archive. It is a molecular text written in a four-letter alphabet of nucleotide bases: adenine, cytosine, guanine, and thymine. That spells out the instructions for building and maintaining living organisms. Every time a cell divides, it copies this text, passing it down to the next generation with occasional subtle mutations. Natural selection acts as the editor, weeding out instructions that lead to failure while preserving and amplifying instructions that confer an advantage in a changing environment. Consider what this means for every living creature alive today. Your DNA contains molecular echoes of ancient battles against long-extinct pathogens, physiological adaptations to ice ages and hothouse climates, and structural blueprints inherited from fish that crawled out of ancient Devonian swamps. When a modern animal possesses camouflage, keen eyesight, or a specialized organ, it is carrying operational solutions to survival problems that were solved millions of years ago by its ancestors. Life does not reinvent itself from scratch with every new generation. It builds upon the accumulated archives of the past, editing an ancient manuscript that has been continuously revised since the dawn of biology. This realization dissolves the illusion that we are separate from the history of our planet or the cosmos at large. We are the direct physical continuation of events that began in the fiery hearts of ancient stars and the bubbling hydrothermal vents of primordial Earth. The past is not a foreign country or a vanished ghost story. It is actively breathing inside your lungs right now. Every heartbeat is powered by chemical reactions refined over eons. Every thought is processed through a neural architecture shaped by the evolutionary pressures faced by your biological forebears. Yet, human beings are uniquely privileged because our species did not stop at biological memory. We evolved brains capable of symbolic thought, language, and culture, allowing us to build an entirely new layer of historical preservation that transcends the slow, stumbling mechanics of genetic mutation. Long before the invention of writing, human beings preserved their history through oral traditions. Epic poems, creation myths, genealogical songs, and tribal histories passed down around flickering campfires from generation to generation. These spoken archives allowed human communities to maintain a sense of identity, continuity, and shared purpose across centuries, binding families and tribes into a collective historical consciousness. When humanity finally invented writing, first through the wedge-shaped cuneiform impressions of ancient Mesopotamia, the hieroglyphs of Egypt, and the brushstrokes of early Asian civilizations, we unlocked a revolutionary way to cheat time. Writing allowed human thoughts, discoveries, laws, and stories to be frozen onto clay tablets, papyrus scrolls, and parchment, shielding them from the inevitable decay of human memory. A person living thousands of years ago could now speak directly to someone in the distant future, whispering across the chasms of time with absolute clarity. When you open a translated copy of an ancient text, whether it is the philosophical musings of Marcus Aurelius, the epic voyages of Homer, or the astronomical observations of Babylonian stargazers, you are performing a magnificent act of temporal resurrection. The physical brain that originally conceived those words has long since turned to dust, but the pattern of thought has been preserved. The path waiting quietly on the page until your eyes swept across the letters and brought those ancient ideas roaring back to life inside the theater of your modern consciousness. In that precise moment, the boundary between past and present collapses entirely. The ancient author is thinking inside your mind, proving that consciousness has the power to leap across centuries and defy the ravages of physical decay. And today, our capacity to archive the past has expanded into the digital realm, creating a global web of interconnected data that stores petabytes of human history, artistic expression, scientific data, and daily trivia. Servers hum in climate-controlled rooms across the planet, holding digitized photographs of our childhoods, recordings of lost voices, high-resolution scans of centuries-old paintings, and massive databases mapping the genetic codes of thousands of species. We live in an era where humanity has built an externalized memory system that dwarfs anything our ancestors could have possibly imagined in their wildest dreams. Yet, this explosion of digital preservation brings its own unique philosophical paradox. We record everything, yet we often feel more disconnected from the deep currents of history than ever before. We are flooded with a relentless, deafening stream of real-time information, notifications, and breaking news that traps our attention entirely within an overstimulated, frantic present moment. In our rush to consume the newest digital update, we risk losing our sense of depth, our awareness of the long, slow, majestic timescales that shape the world we inhabit. To combat this modern amnesia, we must intentionally step back, slow down, and reconnect with the deeper layers of time that surround us on every side. We can look at a tree standing quietly in a park, knowing that its rings are chronicling decades of rainfall, droughts, and changing seasons silently encoded in its wood. We can walk along a rocky shoreline and look at the exposed strata of cliffs, reading the history of ancient seas, tectonic collisions, and vanished ecosystems written in layers of shale and limestone. We can step outside on a clear night, look up at the ancient photons washing over our retinas from distant galaxies, and feel the vertiginous, humbling scale of a universe that remembers every single thing it has ever done. Let us wander even further into the physical implications of this universal memory, exploring how thermodynamics and quantum mechanics intertwine to ensure that no event, no matter how microscopic or seemingly insignificant, can ever be truly erased from existence. We touched earlier upon entropy, the relentless statistical law that dictates the one-way flow of thermodynamic time, driving isolated systems from order toward disorder and providing the universe with its definitive arrow. But let us examine the microscopic flip side of entropy, the reversibility of fundamental physical laws at the level of individual particles. If you were to zoom in infinitely close, passing through the cellular level of biology, down into the atomic structure of molecules, and further still into the subatomic realm of quarks and leptons, you would find that the fundamental equations governing these particles are almost entirely time-symmetric. Maxwell's equations for electromagnetism, Einstein's general relativity, and the Schrödinger equation of quantum mechanics do not contain an arrow of time. In the mathematical formulation of these laws, running the equations backward yields a valid physical scenario just as easily as running them forward. This creates a fascinating philosophical tension at the heart of modern physics. How can a universe built entirely out of time-symmetric, reversible microscopic components exhibit such a stubborn, irreversible macroscopic arrow of time? How does the microscopic world, which knows no distinction between past and future, give rise to the macroscopic world of aging bodies, shattered coffee mugs, and irreversible history? The answer lies in the concept of statistical mechanics and boundary conditions, specifically the extraordinarily low entropy state of the early universe at the moment of the Big Bang. Because the universe began in a state of immense order, with energy and matter packed tightly together in a smooth, low-entropy configuration, there are vastly more ways for the universe to be disordered than ordered. As physical systems evolve, they naturally stumble into these higher probability, more disordered states simply by the blind, random motion of particles colliding and interacting over time. Think of a freshly shuffled deck of cards. A brand new deck comes neatly sorted by suit and numerical order, a very rare, highly ordered arrangement. If you shuffle the deck thoroughly, the cards become randomized. Statistically speaking, almost every possible arrangement of the deck is a messy, disordered mix. It is not because the laws of physics forbid the cards from accidentally shuffling themselves back into numerical order. It is simply that the statistical probability of that happening by chance is so vanishingly small that you could shuffle cards for the rest of eternity and never witness it occur. The arrow of time is therefore an emergent statistical reality born from initial conditions, rather than a fundamental force written into the equations of individual particles. And because entropy increases across the board, every physical interaction leaves a permanent, irreversible thermodynamic footprint on the universe. When you walk across a sandy beach, your footsteps displace sand grains, altering the microarrangements of countless tiny quartz crystals and dissipating microscopic amounts of heat into the environment. That specific arrangement of disturbed sand is an entropic record of your passage. While the wind and tide may eventually smooth the sand over, erasing the macroscopic footprint from view, the microscopic thermal energy radiated away into the atmosphere and ocean carries the permanent statistical signature of that interaction, echoing outward through the infinite network of cosmic cause and effect. This brings us directly back to the concept of information conservation in quantum mechanics. In the quantum realm, the state of a system is represented by a wave function that evolves unitarily over time. Unitary evolution has a strict mathematical consequence. Information is never lost. The future state of a quantum system contains all the information necessary to mathematically reconstruct its exact past state and vice versa. Even when quantum systems interact, become entangled, and appear to lose their individual coherence through a process known as decoherence, where quantum states leak out into the surrounding environment and become scrambled beyond practical recognition, the information is not destroyed. It is simply dispersed into the vast, complex web of environmental correlations. Imagine dropping a drop of blue ink into a swimming pool of clear water. At first, the drop is concentrated and distinct. As it diffuses and swirls through the water, it becomes harder and harder to see, eventually spreading out so thinly that the water looks completely clear again to the naked eye. Has the ink been destroyed? Has it vanished from existence? Absolutely not. Every single molecule of the ink is still present, floating somewhere within the volume of the pool, perfectly conserved. The information has merely been scrambled, dispersed, and integrated into a much larger system, making it extraordinarily difficult for an observer to retrieve, but leaving its objective existence entirely intact. The universe operates on this exact principle on a cosmic scale. When historical events occur, when civilizations rise and fall, when stars flare and die, the physical information describing those events is never truly obliterated. It is diffused, scrambled, encoded, and radiated outward across the vast expanses of spacetime. The photons reflecting off the surface of the Earth today carry information about our world out into the interstellar void, traveling at the speed of light toward distant star systems. Centuries from now, an advanced civilization light years away, if equipped with detectors of unimaginable sensitivity, could theoretically intercept those ancient photons and watch the history of our planet playing out across their telescopes. This means that the universe is a living, breathing, holographic archive where history is eternally preserved in the subtle entanglement of fields and particles. The past is not locked away behind some dead, inaccessible wall of non-existence. It is vibrating silently through every corner of the cosmos, waiting in the starlight, sleeping in the atomic bonds of our bodies, and echoing through the increasing entropy of an expanding universe. As we continue to sit together through the quiet, deep hours of the night, letting these monumental realizations settle into the tranquil rhythms of our breathing, let us release any lingering sorrow or anxiety about the passage of time. We do not need to clutch desperately at the present moment out of fear that it will vanish into nothingness. Every second we experience is safely gathered into the eternal, unshakable architecture of reality. The universe forgets nothing, and the grand, unending story of existence continues to unfold around you and within you, rich with infinite mystery, quiet grace, and eternal promise.